Hello students, hope you are doing well. Let's continue class 21 on the course Linear Algebra and Differential Equations. Today we'll see some systems of differential equation and how to model them, as well as how to solve a certain systems of linear differential equation. Of course, not all differential equations. Our concern will be systems of linear differential equation. So in practice, most applied problems, we can see it here, involve more than one unknown function for their formulation. Yes, we'll see it some formulation and hence require the solution of systems of differential equation, because the applied problem could be modeled by a certain systems of differential equation. And perhaps the simplest way to see how systems naturally arise is to consider the motion of objects in space. See, if this object has certain mass m and is moving under the influence of a force, so the force could have three components, F1t, F2t, and F3t, because we are considering in space. Then just like if you consider Newton's second law of motion, the position of the object at a certain time t will be what? X at t, y at t, and z at t, yeah? Because we are under 3D. This may be represented just like three components to me like this. And of course, it is obtained by solving a certain systems of differential equation. You see, this is differential equation, which is second order. Here also we have second order systems of differential equation, and this one is also second order differential equation. So the difference is, of course, this one is acceleration, the acceleration, because this is a second derivative of a certain object, and this one is also acceleration. This is also acceleration. That's why mass times of acceleration gives you a certain force. Therefore, like the position of the object at time t is obtained by solving these three systems. Okay, these three systems of equations to me. So in this lesson, our main concern will be just like formulation and solutions. We'll formulate just sample, and then of course we have to know how to solve a certain systems of different equations. So as I told you, the main topic to see here is like we have to formulate how problems are formulated. Will be discussed by showing some examples, and how many solutions do we have, if any, does our linear systems of differential equation possesses, as well as how do we find the solution. Okay, so like you are expected to know just like formulation. Okay, and just like if it has solution, how many solutions could it have, and also just like how to find the solution as well. So these are like important points that you should know. See, for example, a formulation of a certain systems of differential equation. Here we have a coupled spring, because this one is like spring one, so K sub 1 is for the spring one and K sub 2 is for the spring 2. This coupled spring mass consists of two masses. This one is mass 1 and the other is mass 2, connected by spring. These are two springs with spring constant K1 and K2 respectively. Then you see, like upon applying a certain mass on this spring, there must be a certain displacement. Yeah, originally the spring was here at x naught, and this one also at y is equal to 0 at y naught. But after applying a certain force, maybe it could be the weight, the springs will be displaced like this, displaced, xt, yt. So this is like the displacement, yeah, displacement. So the position of the original objects are what? Changed. Therefore, like if we say that xt and yt represents the displacement that I showed you the displacement of M1 and M2, just like from their original position. Therefore, the system is in static equilibrium position. And if you remember the Hooke's law and Newton's second law, is by combining the Hooke's law and Newton's second law, yes, we can generate, or we can form the motion of the two masses by these two systems of equations to me. So this one is mass and this one is acceleration to me. And this one is what? K1 times X is what? Hooke's law due to mass 1, because there is like some extension, you can see it here. And of course, here also what? K2 times some extension. Sorry, some extension is what? Y minus X. Y minus X, this one is the extension. Y minus X. If you go back here, like this, here, you see this was like this. So there will be some certain displacement to me. Therefore, like our objective is this, we formulate already a certain differential systems of differential equation. So we have how many systems? We have two systems because we have two differential equations. So we have two systems. So this is like sample formulation of a certain systems of differential equation. Now, when we go to the first order linear system, this our main attention will be on the linear. And here we have systems of differential equations which are linear. Systems of differential equation of this form, we see we have 1, 2, 3 through n. Yeah, 1, 2, then n systems of differential equation. So a system of differential equation is simply written as the form dx1 by dt. This is first derivative to my a1 1t x1t plus a1 2t x2t, and so on through a1 nt xnt plus b1t. So just like remember the systems of linear equation, just analogous to the systems of linear equation. Just this we have like systems of differential equations to me, where these are what? The coefficient, like in the systems of linear equation. In this case, we have aijt, and of course here we have also bit, and these are specified functions. Both are specified functions on a certain interval, which is called the first order linear differential equation. So this system is simply a system of first order linear differential equation. And of course, sometimes this B1t, B2t, or in general, the BIT could be all zero, like that of the homogeneous system, if you remember. So in this case, we'll have also the homogeneous part, or the homogeneous linear differential equation. So they are like similar or analogous to what we have discussed in last classes. And we usually use dxi by dt just by xi bar to show derivative, okay? To show the derivative, okay? These are like notation, no problem. So for example, in the book that we are using, we are mainly using this xi bar, and some other books you may find dxi by dt to me. See, for example, this is a linear, first order linear system, because this is dxi, dx1 by dxt, and this one is dx2 by dx. We can write this as dxi by dt, and if you write like this, it is dx2 by dt. Okay, so like this, so you can see that this is two systems of linear differential, okay, equation. And if these are like b1t, this one is b2t, and we have said that if these two values b1t and b2t are 0, we can obtain the homogeneous system. So this one is what? It's analogous homogeneous, okay, homogeneous, because we don't have this minus cos t and sin t. just only the variables of x1 and x2, the coefficients of x1 and x2. So this is the homogeneous system. And when do we say that a certain systems of linear equation has solution, or like to show whether a certain function is simply the solution to a certain systems of linear equation? Just simply we have to substitute in both sides of the equation, and then finally if they turn it to the same function, we say that it is the given a solution of the differential equation. Otherwise we can say that it is not the solution. For example, it says verify that x1t, which is given by here, and x2t, which is given by here, is solution to these two systems of linear equation. So it is simple. X1t here we have, so we have to find what? X1 prime, yeah, which is like minus 10 is the power of 5t plus 4, no, minus 4, here is minus t. You see, this one is for the derivative, and we have for x itself this one, and minus a times x2, we have this a times of x2. Upon substituting here, maybe you can say this one is 1, this one is 2, and this one is 3. So this one is what? X1 bar is 1, x1 is what? 2, minus a times of x2 is what? 3. So if you substitute, maybe we can obtain the same, otherwise not the same. So if you check it here, as I told you, this one is the derivative that I did. Now we are trying to substitute here, x1t minus a times of x2t is here, and of course this one is what? This one is x1 bar. Therefore, we can say that it is solution. Yeah? We can say that x1 and x2 are the solution for these systems. It says last on the is satisfied by the given function for all t. Therefore, we can say that x2 bar is also minus x1 plus 3 times of x2, yes, which is in the second. You have to also check as well in the second, okay? Not only in the first. This one is for the first. Check for the second equation as well. If it is true, we can say that x1 and x2 are what? The solutions to the given systems of differential equation for both these two. So in this case, they are solutions to me. Okay, the other thing that you have to know is then how to find the solutions of a certain systems of linear equation. For example, consider these two systems of linear equation. Okay, x1 bar, which is equal to a11 x1 plus a1 to x2 plus b1t, which is the non-homogeneous systems. So in this case, just like that of the simultaneous equation, we have to remove a certain variable. Okay, we have to remove or eliminate a certain variable to me. So what we have to do is, because this one is x1 bar, which is like what? Just if you write this as operator, this is d times x1 to me, yeah? Like this. So this one is d times of x1, which is equal to a11 x1 plus a12 x2 plus b1t. If you write the derivatives in terms of the operators, it will be all easy. Then finally, just like if you take this to this one, it will be what? D minus a11, because this one is a11, this one, d minus a11 x1 minus this one, a12 x2 equal to b1t. And here also, instead of this one, because here we have x2 bar means d times of x2. Therefore, like consider this and this one, and you'll obtain like this, minus 2 times, minus a times, minus a to 1, x1 plus d times of minus a to x2, which is equal to b to t. Now we can remove what? Now we can remove x2, just like remember simultaneous, or else it is also possible for you to remove this x1 to me. So just as I told you, D is the differential operator, and the idea behind the solution technique is, as I told you, we can easily eliminate x2 or x1 between these two equations, just like by that of simultaneous equation. For example, if we multiply this equation 9.15 by d minus a22, so that we can cancel this one, just like multiplying equation this 9.16 also a12, then it will be easily removed like the term a2 to me. And adding the result equation, this is the second order constant coefficient of linear differential equation for x1, and of course it will be what? Solvable. Let me show you practically. Suppose just solve the system. This is like good question. So we have first order linear differential equations. These are two systems. Yeah, because we have one and two. Therefore, what you have to do is what? This x1 bar is to mean what? D minus d dx1, which is equal to x1 plus 2 times of x2. But I can write like this: d minus 1 times of what? x1 minus 2 times of x2 is equal to 0. You see? So this one is the first equation, d minus 1 x1 minus 2 times of x. And similarly, you can put it the second equation like this. Now, just like which one is going to be removed, maybe you can get the easiest way. If we want to eliminate x2, first we have to multiply the first equation by what? By d plus 2, and the second equation I have to multiply by what? By number 2. So in this case, upon multiplying the first equation by d plus 2, this will be what? D minus 1 times d plus 2, which is like this, times x1 minus 2 times of d plus 2, x2 equal to 0. So this one is like the first after multiplying by x d plus 2 and adding twice this one also, because this one is 2 times. I should multiply the second equation by 2. Therefore, adding twice of equation 9.110 to this equation, it will eliminate easily x2 to me. That's right. Therefore, you will remain what? With the first equation, that is d plus 2 times d minus 1 x1 minus 4 times of x1. This minus 4 times of x1 is obtained from the second equation to mean. Therefore, like if you multiply d plus 2 by d minus 1, you'll obtain d squared plus d minus 6 times of x1, including this one to mean. Therefore, once we obtain this one, just remember in chapter 8 that we have seen, and it is now possible to find what? To use the auxiliary polynomials to me. Now the auxiliary polynomial is what? Because we have d squared plus d minus 6 times like this. See? D squared plus d minus 6, yeah? Times x1, times x1. Therefore, we have this d squared instead of d squared, we have this r squared plus r minus 6. And upon factoring, it will be r plus 3 and r minus 2. Therefore, the general solution, as you know, is like c1 times e to the power of minus rt. Therefore, here we have minus 3t for the first, c2 is the power of 2t for the second. And once you obtain this solution, x1t, and we can go back to equation 9.19 here, because we obtain x1, and upon substituting x1 here and derivating and just adding with minus to x2, you'll obtain directly x2, or else you can directly go this one, go here, because we already obtain x1, just derivate it, then substitute here, and you'll obtain 2 times of x2, both possible. Therefore, just like from equation 9.19, you'll obtain x to t again. What? X to t is like half of d minus 1 times x1. Now x1 is here. From this, we can substitute x1 here, then derivate d minus 1. Inserting the expression for x1 in this equation into the previous yields what? Half times of dx1 minus x1. That is, we can derivate this one and obtain this one. So this one is what? X2. And here we have what? X1, which means we are solving X1t and X2t. That is considered as the solution for the two systems of linear equation where C1 and C2 are arbitrary coefficients. Likewise, if we have initial value problem for the systems of linear equation, yes, it will be the same as what we have considered, but we have to find the values of the constant C1 and C2. For example, earlier we have seen these two systems, yeah? These two systems, this one as well as this one. But there was no like these conditions, the initial conditions. So what we have to do is, we know that already here we have seen that this is a solution, just like you can refer it back here. This is a solution. But in this case, C1 and C2 were arbitrary constants. Now we can determine exactly what C1 and C2 are. Because X1 at 0 is 1 and X2 at 0 is 0 to mean, which means this is t value, t when t is 0 and t is also 0 for the second. So when t is 0, this will be what? C1 plus C2, and X1 at 0 is 1. So this is what? C1 equal to C1 plus C2. How about this? 0 equal to half of minus 4C1 plus C2. This is the C1 at 0 equal to minus 4C1 plus C2. So here we have second equation, and here we have first equation. We can solve them simultaneously, and here we can, this is the coefficient, and you can obtain C1 is 1 over 5 and C2 is 4 over 5. Then finally have to substitute the values of C1 and C2 in the equation, and C1 x1 by t and x2 by t is here. So as you can see, this is what the specific solution. Specific solution for the systems of linear equation. And lastly, we have to see the vector formation of systems of linear equation, just like nothing new. If you remember the matrix representation of systems of linear equation, if you remember this, where this one is a quotient matrix, x is a variable, and this one is a constant matrix, all the same. However, this is what in systems of differential equations. You can see systems of differential equation. So this can be equivalently written as ax equal to b like this. But instead of ax plus b now, because these are differential equations, these are like considered as in b for this case, yeah, remember. And however, these are what with coefficients considered as a at t and x at t are what the variables to mean. So x is here, you can see it. X is the variables x1, x2, x3 through xn. X bar is derivative, and 8 is like the coefficient, okay, the coefficient, and bt is like simply b1t, b2t, just like imagine the non-homogeneous systems of differential equation. Notice that this x bar, and b are column and vectors. And if we let v sub ni denote the set of all column and vector functions defined on an interval I, then define addition and scalar multiplication within this set in the same manner as for the column vector. So the following rules concerning v sub ni will be needed in the remaining section. Just like Vni is what? A vector space, and as it tells you here, this Vn is a set of column and vectors, okay? So here we have maybe x1 of t, like this, maybe this could be x2 of t, and so on, okay? This is what Vni. And this Vni is a vector space, just like interested reader can check why this one is a vector space. Just remember the 10 axioms. And here we have another important term that you should know, the Wronskian. If we have x1t, x2t through xnt, be vectors in BNI, just same as what I showed you. Then the Ron scan of this vectors is simply written as W of the matrix formed by these vectors is defined as the Ron scan of x1, x2, xn of t, and the Ron scan is simply the determinant, okay, the determinant of the column vectors or matrix. So just remember this one, okay, the Ron scan is the determinant. And here we have notice that the word the Ron scan introduced in this definition refers to the column vector function, you see, in the vector space BNI, whereas the Ron scan defined previously in the text refers to the function. Of course, yeah, that was CNI. If you remember, in that case, the Ron scan, yeah, in here was like simply what defined as a the determinant of some solution y1 of t, and this one is its derivative of t, y2 of t, maybe derivative. Now we are not supposed to derive like this. So we are not supposed to derive like this, but simply we are going to find the determinant of the matrix which is formed by the columns in the vector space BNI. Just you can see it here. Simple example. Determine the Ron scan. We have x1t, x2t. Now the Ron scan is what? Is simply the determinant of this one is what? x1t. This one is x2t. x2t is what? 3 sine t cos t, and x1t is e raised t to e raised t. Therefore, upon taking the determinant is what? This times this, which is e raised t times cos t minus 2 times e raised t times 3 sine t. That is 6 times this. This is the Ron scan. And if we have x1t, x2t through xnt, which are vectors in BNI, if the Ron scan at certain point t naught is non-zero, which means if the Ron scan is non-zero, okay, if the Ron scan is different from zero, which implies these column vectors are what? Linearly independent. Linearly independent. Okay, implies the set contains are what? Linearly independent. For example, in the previous example, we have this x1t and x2t. Can we say that this x1t and x2t are what? Linearly independent? What we have to do is we have to find the Ron scan, which is a determinant of the matrix x1t and x2t, and this is what we have obtained earlier. Can see it here. Then is non-zero, yeah. This one is non-zero. For example, if t is 0, you can substitute here. If t is equal to 0, cos 0 is 1, yeah. This is 0, so 1 times e raised t is a power of 0 is 1, yeah. This will be 1. If 1, which is like different from 0, we can say that these are linearly independent, which means x1t and x2 are what? Linearly independent. Lastly, just what you have to see is given n by n matrix of function of at, the function t from the b sub ni to b sub ni defined by t of x, which is equal to the product of at times x is simply linear transformation. Just like remember when it is linear transformation, and of course it is defined in the vector space b sub ni. And the proof is easier if we take two column n vectors x and y. We have that t of x plus y is what? By definition, it is a times x, therefore it is a times of x plus y. But like we know that matrix, the product of this one is what? Matrix is distributive, yeah, because we are under the vector space ax plus ay, and by definition ax is tx plus ty. This is the first condition that we show for the linearity. And second is what? T times of cx is the a times of cx, which is c times of x, which is also c times of the x, which is the second criteria. Therefore, we can say that from conditions 1 and 2, we can say that t is linear transform to me. T, which is defined here from the vector space V sub Ni to itself is simply a vector space domain. So this is all what we have for today, and we'll give you exercise for you. All the best. Bye.